forms of Maxwell's equations that you end up with these differential relationships between the electric and the magnetic fields. So I'm going to write two of them down and then work from there to create a more complete relationship between electric and magnetic fields. So one of the relationships that I just deduced was this one. And the one that I didn't deduce for you, but I'm going to write down here anyway, is dBc dx equals O. Yeah, I'll write it out in MKS. This is 1 over c squared.
Or 1 over c in Gaussian.
1 over c.
In Gaussian.
1 over c squared. Yes, it's
1 over c squared.
It's 1 over c, but then I need a c
Gaussian,
over there. Okay, each of those deduced from integral form of Maxwell's equation. Yeah.
On the first equation you wrote there, there's dy dx.
Yes. It is. This is, I rotated the axis. Thank you. Is the other one right? dc dx, dy dt. Yeah, that's what I wanted. All right. What I want to do is connect those two, and by connecting them, I'm going to end up with a wave equation. I think the electric field is what I'll come up with, but I could do it for any of either of the fields. So I'm going to take a derivative of this with respect to x. Because these are partials, I can just switch the orders of the derivatives. Oh, look. I dropped a minus sign. And a constant. The wave equation. This is just the in MKS, right? This is just the y component of the electric field. I can equally well, if I want to go through all of that work, come up with the x, y, and z components of the electric field and the components of the magnetic field as well. So this yields a wave that travels at the speed of light. And that was Maxwell's actually big achievement. He recognized the symmetry that might apply if in Ampere's law, if we included the rate of change of flux of the electric field. That then actually led to this, which he realized predicted that electromagnetic waves would travel at square root of epsilon naught mu naught, 1 over the square root of that. And then it took about 40 years for Hertz to actually demonstrate that electromagnetic waves travel at the speed of light, actually travel at that speed. And as an historical aside, Hertz, when he was finishing those experiments, found that his spark gaps, he needed to make a spark in order to get his electromagnetic wave. His spark gap fired more easily when he shined light on the gap. And what he actually was making was the first observation of the photoelectric effect. But he just included it, he said, oh, if you shine light on it, then it sparks more easily. I think that's sort of cool. Okay, I don't have my watch. What time is it?
45.
45. I heard something. Yeah, I thought it was Josh, but apparently not. Let's take a 10-minute break now.